where we foray into series, which is the sum of sequences. And we'll go into the parametric function in the calculator in a few minutes again. This technique will work. It's just, I'm still aggravated that I couldn't, I'm missing something of like why it wasn't working before, but I'll get it straightened out at some point. This crazy itch on my leg is killing me. I think that mosquito must have got me. I'm like dying here. Arithmetic sequences are in the form of a linear function, a sub 1 plus d of n, or a sub 1 plus d of n minus 1, depending on what your lower bounds of summation are. We'll get to that in a second and what all that stuff means. But there is an idea of like, well, do we want a lower bound to be equal to 0 or 1? Well, 0 is a convenient number, yes. And it leads to a simpler equation or expression, yes. But if we're talking about the set of positive integers as being the domain for all of our sequences, then any case in which the lower bound on your summation is equal to 1 is going to make more sense for us. All right, so arithmetic, geometric, we'll get to that. I'm going to take you through all that in a sec. The other helpful rules, I don't think they're anything more than common sense, because you have a constant multiple of c that can be factored out. So that happens for limits, derivatives, antiderivatives, algebraic expressions. So why wouldn't it happen for summation? All right. The sum of a sum or difference can be broken up also. All right. So let me first talk to you about the structure of that summation. I'll just do it off on the top here. So what we're dealing with is this notation, and it's some funky notation. I mean, there's no other way around it. But if you understand what each component is telling us, then it's really not that bad. All right, the a sub n is a sequence. And that can vary from problem to problem. All right, we've dealt with a few of them already. Some of the problems on the previous page were pretty intricate, but each one of them represented a sequence of some kind. All right, we default to a sub n because you could be dealing with different sequences like b sub n, c sub n, but if we're defining a single rule, it just makes sense to stick with one of them. It stands for index, but that has never helped anyone ever. So we're going to say I represents the initial value, the initial term of the sequence. And then the n on the top is the final term. So n is the final term. Bearing in mind that it could be left variable. So you might be dealing with a particular value, I equals 1, and then it goes to 5, for example. That would not be an infinite series, right? If it's going from 1 to infinity or n, then that's indicating that it is an infinite situation, all right? So if we leave it variable on the top, then what we're saying is that we're allowing for this to be true for any possible value of n, right? So it allows for all finite cases, including that of infinity, right? If we say specifically infinity, then what I would want to know is the sum of all of the values from the first one all the way up to the last one that could exist, all right? So how do we determine convergence and divergence of a series? It's a really challenging concept because there's so many different approaches that could be taken. And I have a flow chart for you later in the packet. But we're not there yet because I haven't even showed you the first strategy. One thing that you might default to is using a calculator approach, and I'll show you that in a few minutes, but even that can be somewhat limiting. All right, so you have a series here that's going from 1 to infinity, which means that I'm taking my sequence 3 over 2 to the nth power, starting off by plugging in a 1, that gives me 3 over 2. Then I plug in a 2, that gives me 3 over 4, then a 3, that gives me 3 over 8, and so on. All right? One thing that you could do is find what are called partial sums, the first 10 partial sums of the sequence. All right? There's no real other way to put it. It's a royal pain in the ass. It's not something that you want to have to do very frequently, but we'll do it this one time just so you can get a sense of what the concept is really telling us. Because if you can get an idea of what, they call it partial sums, I call it rolling sums. If you can get a sense of what the rolling sum is for each additional value, then maybe you can get a sense of whether it's closing in on a particular result. All right. So the first partial sum would be the first entry. Now, if the sum is every possible term of a sequence added together, then the partial sum would be something that's part of that. All right. So the second partial sum is going to be the first 2 values added together. Then the first 3 values added together. And the first 4. All right, so obviously not something that you would want to show all the work for, all right? Because I'm only 4 in, I got to go 10, and I'm already like ready to pull the remaining hair out, all right? So we'll do it a little bit quicker in that we'll get a sum, so 3 halves, and then we'll just add the next entry. So 3 halves plus 3/4. So, and I'll math bracket, so 9/4. Then I'll just add the next one to that. So instead of just adding these 3, I know I have these 2, I'll just add the 3/8 to it. 21/8.
Can you also just set all the denominators to 16?
You could, but then the next one you'd have to set them all to 32 and 64 and so on. So 45 over 16. Now, you start looking for a pattern because you want to streamline this as much as you can. And so the denominators, we know that they're just doubling as we go. All right, so when I'm going down the line, we're at the 5th, 6th, 7th, 8th, 9th, and 10th values. Get some commas in there. 32, 64, $1.28, 256. Just recopying what I see above because there's no reason to change it. So we have that. All right. If we could find a pattern in the numerators, then we can avoid having to continuously add these numbers. All right. So you start saying, okay, well, what am I doing here? Adding 6, and then I'm adding, what's that? 12, then 24. So it seems like my numerator is going to be arithmetic in nature, in that I'm adding some multiple of 6. Right? So 6 times 1 plus 6 times 2 plus 6 times 3 plus 6 times 4. So you can do it that way. But even that's probably too much. You don't want to get into that. All right. So the question would be, well, how would you do it in an even easier way? And this is the, I was trying to show you related to something completely different earlier, but in the parametric mode in your calculator, it can very easily handle these kind of computations. All right. So we'll take a minute and do that right now. Maybe you don't want to deal with the fractions. So in which case the decimals are fine. But maybe you do want to have it in fraction form, in which case you'd have to do the math. And so if I were doing it this way, because again, it's plus 6, plus 12, plus 24, right? It seems like we're doubling the value of 6. So you could just add 48. So 45 plus 48, that would give me 93. Hopefully that's right. Plus 96, 189. Plus 192. So 381. Plus 384. And that's again assuming that you wanted to go fraction form. I can't imagine that you would be so set on having a fractional answer that you'd go through all this trouble, but you never know. So 381 times 2 plus 384, 1146. This is disgusting. So 2670, and that's without even concerning myself with reducing or anything like that. All right. So it says, what do you notice about the results? Well, it's getting harder and harder to figure out, but it's approaching 3. Right. So they're approaching the sum. Partial sums are approaching 3. As n approaches infinity. Now you have a rule. If you have a common ratio of the r value, if that r value is less than 1, the absolute value is less than 1, then you could actually apply this rule. But the one issue with this rule is that it relies on your expression, depending on how it's structured, being in the proper format. All right. So if you look back at the geometric series definition, and that's what this is, it's geometric. All right, anytime you're multiplying by a consistent value from term to term, it's considered geometric. We're looking at something that should be modeled like this, but it's not quite like that. All right, so what we would want to do is clean it up. We'd want to manipulate it a little bit. All right, so the first thing I would do is get that 3 out of the way. So 3 times 1/2 to the nth power. All right. So really, there's kind of an intermediate step in there, but I don't think I necessarily need to write it, because I could bring the 2 to the n up and negate the exponent. So it would be 3 times 2 to the negative nth. I guess I could jot that down up here. Little algebraic skill. That's the same as 3 times 2 to the negative nth. that negative exponent tells you to take the reciprocal of the base. So I could make the negative exponent into a positive n by changing the 2 into a 1/2. All right. So what that does is it gives me the a sub 1 value, because if it's in the form that we need it to be in, so n equals 1. Actually, that's a, I guess it's all right. I was going to say it's a typo, because usually I like to have an index of I. Oh, but it's going to infinity, that's why. So a sub 1 times r to the nth power. We could identify the a sub 1, which would be 3, and the r value, which would be 1/2. And so we could get the sum this way. The sum would be 1/2 times 3 over 1 minus 1/2. Which is going to clean up to give us a 3. So you could get it that way too. So this is more of an experimental approach, and this is more of an empirical approach, I guess. But it's not really necessarily 100% required that you determine what the sum is actually converging to. It's really more so, the importance comes from determining whether or not it converges. So you're going to find a recurring theme within this course is making the determination of whether a series converges or diverges, not necessarily what it converges or diverges or converges to specifically. All right, because and it comes down to basically computer programming, because if you have any experience with that, you know that all you need to know is that there's an answer, and then the technology can handle it for you. You could write a program like to do the most complicated calculations, as long as you know that a particular answer exists. You can write a recursive model to help you determine what that answer is. It might take like all the computing power that you have at your at your disposal, but you'll get it. But if you get stuck in an infinite loop, I don't know if you got that error message when you were writing a program. That's always fun, where you're trying to develop a solution to something and it's just spinning the wheels over and over again. And that's because it's a divergent situation. There's no solution that the computer, it's trying to close in on a solution, but it can't because there is nothing to be closed in on. All right, so knowing whether or not a series converges is the key to everything, because at that point you could just write the code to get you to the solution. All right, if it diverges, it doesn't matter what you write. All right. So anyway, we actually already tackled this problem, but you can try it on your own if you want, but really if you just kind of follow back, oh, that n is absurdly high. That shouldn't be like that. That's a typo. Yeah, I mean, I don't know that it's necessary to do this, because if you were to, I mean, it's only the first 5 terms, so it's not that bad, but all you're doing is adding. So you're taking the first 2, then the first 3, the first 4, and then the first 5, and adding them together. So if you feel like you need practice with addition, by all means, go for it. But if you have better things to do with your time,